We're always talking about making AI bigger and smarter. But what if the real secret isn't just about size? What if it's about how we build the highways inside its brain? Well, today we're diving into a really cool breakthrough called Manifold-Constrained Hyper-Connections. It's a whole new blueprint for building AI that's not just more powerful, but, and this is the key part, way more stable. So to really get this, I want you to picture an AI's neural network like a massive city's information highway system. For that AI to learn anything, data has to flow through it smoothly from point A to point B. But as we make these systems more and more complex, they can create the absolute mother of all traffic jams, bringing everything to a grinding halt.
All right, so let's take a look at the standard route, the way we've been doing this for years. This is really the foundation for how information moves through pretty much every modern AI model out there. This standard route is called a residual connection. And the best way to think about it is like a simple, reliable, single-lane bypass road. It's this really clever trick that lets information kind of hop over a layer in the network. That way, the signal doesn't fade or get totally lost, especially in really deep networks. And for the last decade, this has been the gold standard because, well, it's stable and it just works.
But a simple bypass road just isn't going to cut it if you're trying to build a true megacity. So researchers came up with something way more ambitious: hyper-connections. The whole idea was to build a much, much bigger and wider road for all that information. And here's where it gets really interesting. Just look at the difference. We're going from that simple single-lane bypass to this massive 8-lane superhighway. Hyperconnections promised so much more capacity, so much more power. But there's always a but, right? Look at that trade-off. We go from stable to potentially unstable. There's a really big hidden flaw in this new, bigger design.
And that leads us to the billion-dollar question. What on earth happens when you build this incredible superhighway, but you completely forget to add any rules? We're talking no lane markings, no speed limits, just raw, unregulated power.
Well, you get exactly what you'd expect: an inevitable, absolutely catastrophic pileup. It turns out that as these super powerful hyperconnection models get bigger and you feed them more data, they have this nasty habit of becoming incredibly unstable and just crashing.
The researchers put it this way: without any constraints, the information signals that are flying down the superhighway either get amplified into total gibberish or they just fade away into nothing. The whole system basically loses all control over its own information flow.
And when I say amplified, I mean it's just insane. The data shows signals could get boosted by a factor of 3,000. That's not just turning up the volume a little bit. That is a full-blown explosion.
So what you're seeing here is the digital version of a multi-car pileup that just shuts down the entire highway system. The AI's training process completely collapses under the weight of all these exploding signals. So yeah, the superhighway was a great idea, but in practice, it was basically unusable.
But this is where our hero enters the story: Manifold-Constrained Hyper-Connections, or mHC for short. And the genius of it is, it's not about tearing down that superhighway. Oh no. It's about installing a brilliant traffic management system to get everything under control.
The solution is just so elegant. You keep the wide, powerful superhighway, but then you introduce a set of really strict, mathematically defined traffic rules. And then an algorithm acts like the ultimate traffic controller, enforcing perfect balance. This allows all that information to flow at super high speeds, but with zero crashes.
Now, the secret sauce here is this mathematical rulebook called a doubly stochastic matrix. And look, all you really need to know is that it's a set of rules that guarantees a perfect conservation of energy. It means the amount of information signal going in is exactly the same as the amount coming out. No more explosions, no more signals just vanishing, perfect balance.
And this visual just says it all, doesn't it? On the left, you can see that chaotic, unpredictable, all over the place flow of the original hyperconnections. But then look on the right. With the mHC rules in place, you get this clean, stable, and perfectly balanced flow of information. It's literally order restored from chaos.
Okay, so it solves the stability problem. That's fantastic. But the big question is, does it actually make the AI any better? The researchers put mHC to the test to see if this new, stable highway actually leads to a smarter destination.
And wow, the results are seriously impressive. For a massive 27 billion parameter model, HMIC didn't just keep up with the old way, it blew past it, improving performance pretty much across the board. I mean, look at those gains in reasoning and math, over 7%. This is the proof.
A stable information flow directly translates to a smarter, more capable AI.
Of course, the key question is always about scale, right? Does this trick still work when you build one of those truly giant models of the future? And the answer is a huge yes. The benefits and, crucially, the stability hold true as the models get bigger and bigger, even when they're trained on over 1 trillion tokens of data. This isn't just some neat lab experiment. It's a real solution for industrial-scale AI. And get this, here's the kicker. All of this, the stability, the huge performance gains, the scalability, it all comes at an astonishingly low cost. Putting mHC into the model adds less than 7% to the training time. I mean, that's an incredible trade-off. You're building a fundamentally better, more reliable model for a tiny bit of extra compute.
So what does all this mean for the road ahead? Well, this isn't just some small, incremental improvement. This is a real shift in how we think about designing the very architecture of an AI's brain.
As the paper itself concludes, this kind of work opens up totally new pathways for the next generation of AI. It's about finally understanding that the structure of the network, the actual topology of the highway, is just as important as how big the engine is.
And that really just leaves us with a fascinating final thought. For years, we've been pushing the limits of scale, and we keep running into these walls of instability. But if we can now build these massive AI systems on truly stable foundations, how high can we actually build? What becomes possible when the fear of a system-wide crash is finally engineered away?